Yeah, welcome everyone to day 7 of dualities in topology and algebra. Somnath will begin with his third session today. It's on rational homotopy groups. Over to you, Somnath.
All right. Thanks, Anand. So yeah, so this is the third lecture in my portion of the like lecture series. So I'm going to talk about rational homotopy groups, and to a large extent, I'm going to talk about minimal models, how you construct minimal models, and in between you'll see a small sort of duality, if you want to call it that, between certain algebraic extensions of DGAs versus principal fibrations on the topology side. Okay. Okay, so let me begin. Okay, so I want to recall, I want to start by recalling what's called the Postnikov tower. uh, some of you, at least the topologists in the audience, would know this, but it's essential for what I'm going to talk about, so I'll recall it very quickly. I'm going to assume my spaces are connected CW complexes. So a Postnikov tower for a connected CW complex is the following data. So what is it? X is your space, and then you have a tower of spaces x0, which is essentially a point, and then you have x1, x2, x3, and you have maps between xn to xn minus 1, maps between xn minus 1 to xn minus 2, these vertical arrows, and then maps from x to the corresponding xi's. Okay. And so this data is not just this collection of maps and spaces, they have certain specific properties that they should satisfy. So the first one is that the ith homotopy group of the nth space in this list, xn, is 0 if I is bigger than the index n. Okay. All right. The second property says that these slanted maps from x to xn is not any map, it's a map which induces isomorphisms on the lower homotopy groups, meaning they are isomorphic on the ith homotopy groups from x to xn when I is less than or equal to n. You see, because if I is bigger than n, this is 0 anyway, and you do not expect this to be an isomorphism, but you expect it to be an isomorphism in the range I less than or equal to n. That's the second property. And the third property is that each of these vertical maps, these are fibrations. Okay, so xn to xn minus 1 is a fibration, and the fiber is a very special kind of a space. It's an Eilenberg-MacLane space, which you have seen in Samik's talk. So this is a fibration with fiber k pi n x n. So the group that is sitting in here is the nth homotopy group of the starting space x. Okay? So I mean, these can be constructed, like fairly naturally if you have seen CW complexes. If you want, you can have a look at any standard text like Hatcher or Spanier where they talk about this. So as perhaps the simplest example of such a thing, if your space X is an Eilenberg-MacLane space, KAN, then the xi is basically a point for I less than n, because you want it to be of the right homotopy type. And then clearly, whenever I is bigger than or equal to n, all the xi's are the same and they're basically KAN. And that clearly satisfies all the three properties. So an Eilenberg-MacLane space will simply be, you take that and put it in the nth level, and then all the higher levels are the same KAN and the lower levels are points. And that is the Postnikov tower for an Eilenberg-MacLane space. Okay. Okay, so for the things we'll be interested in, our spaces are going to be simply connected. So it turns out that if X is simply connected, then this fibration xn to xn minus 1 is what's called a principal k pi n x comma n fibration. So it can be equivalently described as saying that this is a fibration which is obtained by pulling back the path space fibration. So remember, you have a path space fibration from the paths on k pi n x n to k pi n x n, and the fiber being another Eilenberg-MacLane space. So if this fibration xn to xn minus 1 comes as a pullback from that, then you can declare this to be a principal fibration. So another way to interpret this is to say that the fundamental group of xn minus 1 acts trivially on the homology of this space, okay, on the homology of the fiber. Anyway, so this is just a fine point, but and for those who have seen this, you probably know all of this. So if there are no questions, let me move on to what we are going to do with this. Okay. Okay. So yeah, so I want to talk about rationalization and in particular rationalization of spaces. But remember, the goal is not only to talk about how to rationalize spaces. We did discuss some examples of that. The goal is also to be able to connect everything with computing the rational homotopy groups of a space on one hand, which are the usual homotopy groups of the rationalization. But you also want to be able to talk about the rational cohomology of a space, which turns out to be the usual cohomology of, of the rationalization if your space is simply connected. So we want to be able to talk about all of these at the same time using what's called minimal models. So that is the goal that we have in mind. So yeah, in general, what you saw here, although I didn't say it explicitly, is that a space can be thought of as a twisted product of these Eilenberg-MacLane spaces. So a general space X is not a product of k pi n x n's for obvious reasons. So in general, it's sort of a fibration at each stage, and you're building the space up, starting with k pi 1 x1, followed by k pi 2 x2, but they're sort of twisted in. Okay. Excuse me. So yeah, so one calculation that one often does, and one sort of does this by induction, and this is an exercise for the students who know a bit of spectral sequence and so on, is that you can show that if you take the Eilenberg-MacLane space KZN and compute its rational cohomology, it turns out to have a very nice description, that it's Q alpha, where alpha is an element of degree n, and this means it's a polynomial ring with a variable alpha placed in formal degree n. On the other hand, if n is odd here, then this cohomology ring turns out to be Q alpha mod alpha square. So you see, alpha is an odd variable here because alpha is formal degree n. So alpha square is 0. If you think of graded commutativity over Q, then alpha wedge alpha is minus of alpha wedge alpha. So it's simply that. So you can interpret both of these as the free graded commutative algebra on a generator alpha of degree n. Both of these. Okay. So that's what the cohomology ring of KZN is rationally. On the other hand, one can also calculate the usual, and forget the z, but z means the integral cohomology of KQN, and KQN can be constructed either through the usual means, or you can, but we'll interpret it in a different way right now. So this cohomology also turns out to be the same as what we have up here. If n is even, you get this, and if n is odd, you get this. Okay. So what you realize is that the cohomology of this space matches up with the usual cohomology of KZN tensor Q. Okay, and so one way of interpreting this statement is saying that KQN is the rationalization of KZN. Okay, I mean, this is almost immediate from the definition that the pi n's are z at degree, pi k is z in degree n only, and then pi k is q in degree n, and if you rationalize that, you get q. So it's expected that this is the rationalization. Okay, so the advantage of doing things rationally is that the cohomology of this becomes very easy to describe rather than the cohomology of this one. Okay, so let me talk about odd spheres. Well, I'll talk about spheres in general throughout this talk, also at the very end, because these are the first examples one usually discusses. So if you look at the rational homotopy groups of a sphere, what are they? Well, so this is it's a result attributed to Serre, who says that pi k of Sn when you tensor with Q is isomorphic to Q if and only if k is equal to n. So for odd spheres, the only time you see a non-torsion, like a non-torsion subgroup of the homotopy group is when k is equal to n. So this effectively means that all the other homotopy groups of Sn for n odd are torsion. Okay. All right. So in particular, you can think of Sn sitting inside KZN because KZN is constructed by taking Sn and then killing higher homotopy groups, and KZN can be rationalized to KQN. So in particular, since both, if you take the homotopy groups of Sn and then rationalize, that's the same as the homotopy group of KQN. It turns out that KQN is a rationalization of Sn when n is odd. Okay. So this is just an example connecting with other things we have done. This may not necessarily be important for exactly what we'll talk about today. So what about even spheres? This is slightly more involved than the odd spheres because, again, due to Sayre, we know that the rational homotopy groups of Sn, if n is even. So again, when I say odd here, n is odd, and when I say even here, n is even. I didn't make it explicit, but just make a note of that. So this is isomorphic to Q if and only if K is in these two values, n and 2n minus 1. And you have already seen this in basic algebraic topology, that pi2 of S2 is Z, and pi3 of S2 is also Z. That's because of the existence of the Hopf map, which is a generator of pi3 of S2. So this is essentially a generalization of that fact, saying that the only places where you have Q and Q, or integrally Z and Z, are pi n of Sn and pi 2n minus 1 of Sn. Okay. So in particular, if you were to rationalize Snq, or if you were to rationalize the sphere Sn where n is even, and this is what I was calling the rationalization, you expect it to be some sort of a twisted product of kqn and kq2n minus 1, right? Because these are the only non-trivial homotopy groups of Snq. Okay. So yeah, so we might talk about this particular thing for S2 later on, but this is just to connect with what rationalization does. And so the fact that Eilenberg-MacLane spaces behave algebraically in pretty much the same manner, no matter what is, whether n is even or odd, is sort of an important key in the computations. Okay. So I want to, yeah, so to connect all of these things with the DGA models that we have, the CDGA models, and to connect up with the Postnikov tower, I want to talk a little bit about principal fibrations. Okay. Okay, so principal fibrations are, so what is a principal fibration? Well, I said a little bit about that at the beginning. So you have a fibration E to B. You can take it to be a Sayre fibration if you want. You have a fibration E to B, and it's called a principal K pi n fibration. So forget the word principal. It's a K pi n fibration, means that this is a fibration where the fiber is K pi n, where pi is an abelian group. And being principal means one of the two things. As I said, in our case, B is going to be simply connected, in which case this is going to be automatic. But otherwise, what this means is that you take a fibration with fiber K pi n and you ask whether it arises as a pullback of the path space fibration. And the path space fibration, remember, is paths on K pi n mapping down to K pi n, where the fiber is omega of K pi n, which is itself another Eilenberg-MacLane space, right? Sorry, you take, so you take paths on, sorry, there's a shift by one, yeah. So you want the fiber to be K pi n, so you want to map to the paths of K pi n plus 1, okay. So yeah, so if a K pi n fibration arises from the pullback of such a path space fibration, you call it principal. For us, all that we're going to mean here is that whenever you have a fibration, there's an action of pi 1 of B on the fiber. And this basically comes from path lifting, and this we have seen in Samik's talk. So we want the action of pi 1b on the fiber or on the homology of the fiber to be trivial. That is what we want in the applications, and any such fibration has that property. That's all I require from this discussion. Okay, nothing more, nothing less. So whenever you have a fibration and the fundamental group of the base acts trivially on the homology of the fiber, because pi 1 of B acts on F, so pi 1 of B also induces an action on the homology of the fiber, and if that action is trivial, then Sayre spectral sequence with rational coefficients in cohomology gives you a recipe of calculating the cohomology of the total space in terms of cohomology of the base and cohomology of the fiber. Okay, so for those who have not seen spectral sequence, this is a gadget which helps you calculate. The Sayre spectral sequence in cohomology, for example, helps you calculate the cohomology of the total space in terms of things you a priori know well, which are the cohomology of the base and the cohomology of the fiber. Again, this is it's like a black box if you haven't seen it earlier, but just take it for what it is. Okay. So the point here is that if B is simply connected, then all these things that we're talking about, pi1 B acting trivially, is automatically satisfied. So obviously you have such a sequence, and you have to calculate the various pages. So the first thing that you get is the E2 page, and the pqth entry of the E2 page is this entry. It is the pth cohomology of B with coefficients in the qth cohomology of k pi n, but the coefficient of that is computed using q. So this q is saying you calculate the qth rational cohomology of k pi n, take that as the coefficients, and then calculate the pth cohomology of B, and that is your pqth term. Okay, and then there are differentials, which are arrows which you have to compute at each page to go to the next page, which is E3, and so on and so forth. So here, due to the special nature of things, it turns out, so again, I mean, just as a sort of a remark for those who have not seen spectral sequences at all, if you haven't seen it, don't be too worried. At the end of this entire slide, we're going to take home one particular statement, and that's all we're going to need moving forward. So treat it as a black box. For those who have seen it, this is going to be very easy and mundane, perhaps. Okay. So the structure of this spectral sequence at the E2 page is determined by the first non-zero differential, and that essentially goes from this thing, which is what? Which is basically look at H0, E0 N at page 2. So E0N2, which is this, because H0 of B is just whatever the coefficient you are, because B is path connected. And then that goes to En plus 1, 0. And N plus 1, 0 is Hn plus 1 of B with coefficients in Q, which is just Q. So this is the first non-zero differential. Why? Because you see this space is n minus 1 connected. So it has no n minus 1, it has no homotopy groups up to n minus 1, and hence no homology and cohomology up to n minus 1. So this is the first non-zero cohomology group of k pi n. And so this is the first non-zero differential that you have to worry about. But you see, what is this thing? Well, this, again, you have seen this in as part of how singular cohomology can be represented, that the nth cohomology of k pi n is nothing but homomorphisms from pi to q, because this can be represented as homotopy class of maps from k pi n to kqn. But that itself can be identified with homomorphisms from pi to q. Okay, so effectively this term is nothing but homomorphism from pi to q, and this is a differential which is mapping this group of homomorphisms to the n plus 1th cohomology of B. Okay. And so effectively now what are we saying? See, we are saying you look at the, so this is almost like pi star, so to speak, right? So giving an element from here to here is the same thing as determining an element from Hn plus 1 of B with Q coefficients tensor pi. This is just the usual adjunction, right? If you have a map from B star to A, that is nothing but an element of A tensor B. So I'm using that practically, okay? So this differential determines an element here, but here there are two basic things that you can use, and I'll just state them quickly because they are really basic. The first is that what is this quantity? So for those who have played around with coefficients and so on, this is basically the n plus 1th cohomology of base with this as my new coefficient ring, and this is just universal coefficient formula, okay? And because Q is a field, so whenever you do these things, there's no extra terms to worry about. So this is literally this. So I can replace this entire thing and think of the class of Dn plus 1 as an element of n plus 1th cohomology of B with this as my coefficient. Okay, okay, that's the first reduction. Second is, of course, if I now assume that pi is actually a rational vector space. So far pi was an abelian group. Excuse me. But if pi is a rational vector space of finite dimension, then I can also conclude that Q tensor pi over Z is nothing but pi. Okay. So then I can basically, with this assumption that pi is a rational vector space of finite dimension, I can replace this entire thing with pi, right? So effectively, what I'm saying is, given such a principle k pi and fibration, this is the first non-zero differential, and in fact this is the only map that you have to sort of sort out in order to calculate this thing. So it's determined by the group pi, which in our case is going to be a finite dimensional rational vector space, and this element, which is an element now in the n plus 1th cohomology of B with coefficients in pi, because I can identify this with pi. Okay. Okay. So that's a topological side. The small duality that I said I'll talk about is this: that on the one hand you have these kind of principal fibrations which are determined by these two pieces of data. So the upshot that I was saying was this: that we are talking about such fibrations and they're determined by this pair, pi and this class. Okay. So yeah, so I mean, there's a small remark here, but I'll skip that. If there's time at the end, I'll come back to this. So I want to move to the algebra side, sorry, and then talk about what is the analog of this on the algebra side. Are there any questions?
Somnath,
Yeah.
a small comment.
Yeah.
This, there's two isomorphisms you displayed. You don't need the finiteness of pi for the isomorphism. That's always true because pi is a rational space. You need the finiteness for the first isomorphism to move the pi inside. I think. Because if you have a rational vector space in your tensor with Q, it doesn't change that.
Oh,
so as long as
yes, okay,
I think it's,
right. If you are thinking of just as a general, yeah, because if it's not finitely generated, then you will have some trouble.
Doesn't matter. Yeah, you won't be able to move it inside. That's the problem.
Yeah, I see. Yeah.
That's all. It's a small thing.
Yeah, if it's like an infinite direct product, then you'll run into trouble.
Correct.
Yes.
Correct.
Yes.
Yeah.
Okay. Yes. Thanks. Yeah. Thanks. So, any other questions or comments? Okay, so yeah, so I want to talk about the algebra side of things. And so on the algebra side, you have what's called HIRSCH extensions. So I think in most of the modern books, they call it a relative Sullivan algebra. So this is the notation that Morgan and Griffiths use. But nonetheless, I'll explain what it is. So again, you assume that pi is a finite dimensional rational vector space. And you are given an element alpha, which is closed. So we were given an element in the n+1th cohomology of B with coefficients in pi. Okay. And so here we construct what's called the HIRSCH extension of this model. Remember, we constructed this APLB. So these were the piecewise polynomial forms with Q coefficients built out of simplices first and then extended. So how do you do this? Well, you basically construct a new CDGA, which is the old CDGA APLB, and you tensor that with the free graded commutative algebra generated by pi star. So pi star is the dual as a vector space of pi. Okay, but you place pi star, all of the entire pi star, in degree n. That is the thing. So this is, think of this as wedge V, where V is one entire big vector space placed in degree n. And this is, and you have to define a D here, and the D here is defined to be whatever it was on APLB. So D restricted to terms of the form alpha tensor 1 or A tensor 1 is already DA tensor 1, nothing changes. So that's the first part, okay. But what about D of something here? So yeah, so pi star is placed in degree n, but D from pi star to this thing will actually go into, so see, this is placed in degree n, so this will go into n+1 degree pieces in the model for B. So this is going to APLB n+1, and this is such that the image of this lies in closed forms here, and in fact it induces alpha, okay, because anything here can be thought of as this tensor pi, and then you can sort of the usual thing we talked about, move it inside. So you want this D to map here to closed forms, and such that this D induces the map alpha. So this is how we are identifying alpha with D, okay, and the class of alpha. So once it's a closed form, it induces an element in Hn+1 of B. Remember, APLB is quasi-isomorphic. So APLB computes the cohomology of B, right? So whatever this map is, it induces the same cohomology class as that of alpha. So once we have such a data, we can construct such a CDGA, and this is called a HIRSCH extension of the original CDGA APLB, all right? So here are two facts which, so you can look at Griffiths and Morgan, for example, they discuss it this way. So I'll just state them because we need them for things to follow. So two HIRSCH extensions associated with maps to closed forms, which represent the same element in cohomology, are isomorphic. So here, of course, you could choose different sort of representatives for this class of alpha, or you represent this by two different maps which induce the same alpha, it turns out both these models will be isomorphic. Moreover, there's a bijection between principal fibrations over B with fiber k pi n and Hirsch extensions of APLB constructed in this form. So you're basically taking the old model of B and you're adding in a generator, adding in new generators. I mean, this could be more than Q. So whatever the dimension is, you're adding in those many new generators in degree n. And then you're defining D to be modeled by this data of alpha. So so this was the small duality that I was referring to. So principal fibrations over B with suitable fibers can be identified with these kind of CDGA extensions of the model for B. Okay. So we're going to use this back and forth now, moving forward, right? Okay. So what's the construction for minimal models of a space? Well, we'll refer back to the Postnikov tower all the time. So if you have a principal fibration of this form, you consider the data that pi is an abelian group, because in general, the things that appear as the fibers of xn to xn minus 1 are going to be pi n of the space X, right? And that's typically an abelian group. It's not going to be a rational vector space. But we're going to assume that it's an abelian group such that when you tensor with Q, this of course becomes a rational vector space, and we want this to be finite dimensional. Okay. So this was already, I think, in place when we did that. That remark earlier. So we are going to assume that it's an abelian group which, when you tensor with Q, is a finite dimensional rational vector space. And suppose we have chosen a minimal model for this thing. So recall the minimal model was defined to be a minimal CDGA and a map to the piecewise polynomial forms on B, such that this was a quasi-isomorphism, right? So suppose you have made a choice of a minimal model to this thing, and we made the remark earlier that any two minimal models are isomorphic, so I can talk about the minimal model. And there is this other data, right? So usually this is called the K invariant because of how these are constructed from the tower. So we have this data, right? We have a class in n+1th cohomology of B with coefficients in pi. So we have these three things. So given these three things, I want to talk about this theorem, which essentially is going to be a little bit of things that you have to prove. But the point is that the statement is very natural at this point. So you basically define ME, by definition, is going to be a Hirsch extension corresponding to the data above. So essentially you replace APLB with this model, and then you basically want to play around with, see, this is quasi-isomorphic to this. And since this computes the cohomology of B, this will also compute the cohomology of B. So you can construct a Hirsch extension with MB instead, the minimal model of B. And this looks like this, right? So it's going to be the minimal model of B, tensor wedge V star, comma D, because V star is going to be what I replace the dual of this with, and so that is V star. Right? So if pi was already a Q vector space, then I do not really get anything here. I just get back pi, but otherwise this is what I want. So then the claim is that this Hirsch extension is a minimal model for E. In other words, there is a map rho E from the minimal model of, so I'm calling this the minimal model, but it will be a minimal model after I state the theorem. So it's a bit presumptuous of me to call it the minimal model, but I'm calling it so because it will be so. Okay? So there is a map rho E from this to APL E, the piecewise polynomial forms on E, such that the first is that this is a minimal model for E via this map. The second is that there is a commutative diagram of the following sort. So you have the minimal model of B mapping to the piecewise polynomials on B, which is already a choice we made. And then there is this map F upper star, which is the pullback. And this we talked about earlier. And then you have this one. So this one is essentially an inclusion of CDGS, right? Because ME is nothing but an extension of MB by adding in new generators in degree n and extending the differential D in a suitable way. But the D restricted to MB is exactly whatever it was on MB. So this is literally an inclusion of CDGs. And then you have rho E. So there is this commutative diagram, which is also there. So we have this theorem, which tells you how to inductively model, like set up a minimal model for the total space of a fibration, if you know the model for the base and these data. Okay? And so effectively you can now keep working your way up the Postnikov tower, so to speak. And that's practically, if you complete it to its fruition, then we'll get what I'm going to talk about in the next slide. Okay. Are there any questions? Okay. So yeah, so so one property is that okay, so because before I talk about it, so I guess, yeah, so the point here is that you do it at one step, but then you can repeat it. Now you take E to be the base, and then E prime to be the total space, and then K pi prime n plus 1 to be a new principal fibration, and then you can build a model for M E prime, again with these data. Okay, and so you can just keep doing this. So effectively what you're doing is every time you're adding in new generators, which is the free graded commutative algebra generated by V star. And what is V star? V star is nothing but you rationalize pi and then you take its dual. But in our examples, in the Postnikov tower example, pi is going to be pi n of x. Excuse me. So essentially you are taking pi n of x, you're rationalizing that. So you're taking the rational nth homotopy group of x and then you're dualizing that, right? So the new generators that you're adding in are practically one for every element in the basis of pi n x tensor q. So this minimal model by construction is keeping track of how many generators are there, how many basis elements are there of pi n of x tensor q, or in other words, it's keeping track of the dimension of the rational homotopy group set for each n. And as we'll see, it actually keeps track of more data. It's not just that the dimension is being kept track of. So yeah, so the first property is, of course, if this is a minimal model for B, which is denoted by this, then as I just argued, and I'm going to assume B is simply connected, and the cohomologies are finite dimensional for each degree. So I'm assuming J, but you can put upper J, it doesn't matter because they're same. So they have finite rank basically. Okay. So then by the argument that I just outlined, the space V and the rational homotopy groups of the space B, which is pi dot, means this is you take direct sum of pi k B tensor Q. So this is a graded vector space, and V is also a graded vector space, and V is simply the dual of this. Okay, so this is almost by construction, right? Okay. So which is very nice. So this minimal models, as we have seen, are essentially up to isomorphism. There's only one. So if you now talk about the minimal model, then it's saying this V is not just an arbitrary vector space. In fact, you don't have much room for choosing V. It is just what it is. Okay. Okay. So, but here's an even more relevant thing, perhaps, when one talks about minimal CDGs, is that if you have a minimal CDGA, you have a differential D, right? But the differential, you know, it's a free graded commutative algebra, and the differential satisfies the Leibniz rule. Because it satisfies the Leibniz rule, and this is the free graded commutative algebra on V, the differential is determined by what D does to elements on V. Right, so D is a map from wedge V to wedge V, but it's determined by what it does to single elements, because then you can extend by Leibniz rule to wedge of V. So it's enough to know what D does to this. However, I'm saying we can write D as a sum of maps called D1, D2, D3, and so on. What are these DIs? Well, if you think carefully, we have a map from V to wedge of V, or the free commutative algebra generated by V, but then this itself breaks up. So so you see, this itself will break up. So I mean, this is sort of a typo and not a typo at the same time. if you take the wedge of V, this will break up into a lot of things. So there will be a wedge 0 V term, which is just the ground field Q, and then a wedge 1 of V, which is V, and then wedge 2 of V, wedge 3 of V, and so on. Right? So this is all the way. I mean, the reason why this is not entirely a mistake is that when I look at this map D, what is the key property of this map D? This is a minimal CDGA, which means D always maps to wedge 2V or higher. It never sees wedge 0V or wedge 1 of V, right? So that's why when I look at D, D will map to wedge 2 of V, wedge 3 of V on all the higher, and the higher powers, and it will never see the constant term or the linear term. Right? So hence, I look at D, which maps to this thing, and then I project onto the wedge I plus 1 of V. I can always do this. And then this is a map I call DI. So DI is simply the restriction of D. After applying D, I just project it onto the wedge I plus 1 of V, and I call that DI. And this equation simply means you can extend DI now again by Leibniz rule, and this is simply saying D is the sum of these, like these maps, the extended maps. Okay. So yeah, so there's a shift of 1 because D1 is going to map from V to wedge 2 of V. D2 is going to map V to wedge 3 of V and extended by Leibniz. Okay. So again, for degree reasons, if you calculate D square equal to 0, you'll see that this splits into several equations at the same time. And the first equation is D1 squared is 0. The second, because you can now compare which part of the wedge it goes to, and an element here cannot be compared with an element here. They're living in different, spaces, right? And similarly, you have D1, D2 plus D2, D1 is 0. And then D2 squared plus D1, D3 plus D3, D1 is 0, and so on. So you get a whole host of equalities. Okay, but we just focus on D1 because D1 squared is 0. That's a good sign, and by definition D1 is extended to be differential because we know D1 on V, and then we extend D1 on wedge V. Right? So this will be another minimal CDGA, pretty much by construction, right? So starting with the minimal CDGA, you get another minimal CDGA, wedge V, with the new differential, which is D1, and this D1 is often called the quadratic part of D. Okay, so don't let the 1, 2 sort of confuse you. The 1 is just as a bookkeeping device, but D1 is literally the quadratic part of the differential D because it's capturing what is the contribution to wedge 2 of V when you hit an element little v by D. Okay. So we are going to see examples of what this thing is in a moment. So just bear with me. So if I dualize this map, so remember D1 is what? It's basically the map from V to wedge of V and then project that to wedge 2 of V. So D1 is literally a map like this, V to wedge 2 of V. So if I dualize this map, what do I get? Well, I get a map from V star tensor V star to V star. But remember, this is mapping into the, so if I sort of do it correctly, is mapping into, so if the point is, this is mapping into the skew symmetric things, if things were in even degrees, and otherwise it will map to the other kind of things. So if I dualize, what I'm going to get is a graded, so this is going to play the role of a Lie bracket, in the sense this is going to be graded commutative and bracket, and the fact that D1 squared is 0 will tell me that this D1 star can be thought of as a Lie bracket satisfying the graded Jacobi identity. Okay, and this is an exercise you can do even in the usual Lie algebra setting, that if you have a finite dimensional Lie algebra, and that's a map from G tensor G to G, if you dualize, you get a map from G star to wedge 2 of G star, because the initial bracket was skew commutative. And so that the dual of the Lie bracket will satisfy square is equal to 0. So this is exactly the same analogy, and it's the same thing literally. So what I obtain for you here is a Lie algebra on V star. And we'll talk about this, where this Lie algebra comes from, whether it has classical origins, and indeed it does. Okay. So any questions before I move on? So this is a very simple exercise probably for the students in the audience to try and check if you haven't seen it before. That the fact that D1 squared is 0 is the Jacobi, and then the fact that D1 lands in here is going to give you the commutativity or the graded commutativity for thinking of this as a bracket. Okay. Yeah, so there's something called the Whitehead bracket, which I want to recall for the benefit of the people who may not have seen this in topology. So this is something very classical. Yeah, you want to talk about homotopy groups of spaces and further algebraic operations that you can do on those groups. And so the Whitehead bracket basically takes two elements, one in the kth homotopy group of X and another one in the lth homotopy group of X, call them alpha and beta. And then you define a new element denoted by bracket alpha beta, which is an element from the k plus L minus 1 sphere to X. And how is it defined? Well, let's skip the map U for the moment. So it's a composition of two maps. So the first and the latter map is going to be, you take SK wedge SL, and then on the SK part you map by alpha, and on the SL part you map by beta. And since these are based spheres, this defines a map from the wedge of the two spheres to X, right? Yeah, excuse me. So now what about this map? So this map basically is an attaching map. So what do? Well, you look at SK cross SL, and this is just a product of the two spheres. Sorry. So the point is, if you look at the CW structure of this, at least that is the way I find it easiest to describe this map. This has one zero simplex, which is the common point, and then one K simplex, which is the sphere SK, one L simplex or one L disk, or L cell, and one K cell, and then one zero cell. So that at that point you have constructed for yourself SK wedge SL, and then you have to attach a K plus L disk to the SK wedge SL to create this thing. And the attaching map is an attaching map from the boundary of DK plus L to SK wedge SL, and this U is the attaching map. So if you want a concrete example, take the simplest example that you have seen in algebraic topology. Think of what is the map when I put K equal to L equal to 1. So you're trying to construct a torus from a wedge of circles. And the way you do it is you take a rectangular piece of paper, and then you basically first identify the parallel ends to one of the S1s and the other two ends, the two vertical ends to the other copy of S1. So you're attaching a rectangle, which is a disk, by its boundary, which is an S1, by the element A, B, A inverse, B inverse, where A is one of the S1s and B is the other S1, right? It's a commutator. So this is the same idea, okay? So you can take this U map this sphere to the wedge, and then the wedge maps to X just simply by the choices of alpha and beta, and then this is a well-defined element in pi K plus L minus 1 of the space X, okay? So a couple of remarks about what this does. Again, for those in the audience who already know this and are experts, just bear with me. So if K is equal to L is equal to 1, as I indicated here, this is nothing but the commutator. So essentially it's a map from pi 1 cross pi 1 to pi 1, and it's the group commutator. And if K is equal to 1, namely, I want to see what happens if I combine an element of pi 1 with an element of pi L. Well, for degree reasons, it's going to produce an element of pi L, right? Because L plus 1 minus 1 is L. And so it turns out that this is not quite an action, but there's also a related notion of how the fundamental group acts on the higher homotopy groups. That comes by looking at how pi 1x acts on the universal covered by Dieck transformations, and it induces an action. So if K is equal to 1, then this Whitehead bracket is related to the fundamental group acting on the higher homotopy groups. But since we do not need this, I'll not say any more about this, okay? The key things are, the things we need are the following. So you have this graded commutativity, which is alpha beta. If I switch, then I basically have to put a sign, which is minus 1 to the KL, where alpha is in the kth homotopy group, beta is in the lth homotopy group. And I'm putting KL bigger than or equal to 2 here, because even for our examples, our X is going to be simply connected. So we do not have any pi 1 to worry about, okay? See, the point is pi 1 is not abelian, pi L's are abelian. So effectively, this is telling you that somehow, you know, you have to be a little bit careful regarding the entire structure together. But for simply connected things, you simply are dealing with abelian groups all the while. There's no pi1, and so we have very nice formulas. So there's a Jacobi identity as well. So if gamma belongs to pi m of x and alpha beta are chosen as here, then you have this thing, which is the graded Jacobi identity, right? So this is the graded commutativity, and this is graded Jacobi identity. So you take all the cyclic ways of computing three things, and then you have to put some signs, and if you add them, it's 0. Okay. And so one observation here, because of how we described this, it's almost immediate if you think about it, that this Whitehead bracket is 0 if and only if, see, this is a map from some sphere to X. And when is this map 0? This map is 0 if it is null homotopic, meaning if I can, if I can put a disk mapping into X whose boundary is this. But then we already have this disk, right, which is allowing us to create SK cross SL. So if I have this map is 0 if I can extend this to a map from SK cross SL to X. Because if I restrict this to the appropriate sort of attaching map, then I simply get back this. Okay. So this is going to be useful for one of the examples that we'll talk about later on for Lie groups. But yeah, any questions? So this is a quick review of what Whitehead bracket does. But the upshot is that it starts, it sort of gives you something like a Lie algebra when you deal with homotopy groups. And if you want a Lie algebra over a field, what do you do? Well, you tensor everything with Q in view. So that's exactly what we're going to do. Okay? So this is called the rational Lie algebra. So there's one remark about terminology that I want to maybe mention. So in, say, some of the books, they often call it the homotopy Lie algebra, which is a fair term, but keep in mind that like in Pranav's talk, you saw, like homotopy associative algebras, homotopy Lie algebra. So those are different from what this one is, because in the sense, this is the way it's defined, this is going to be a direct Lie algebra. And it's not to be confused with Lie infinity algebras, okay? Although there is a connection. Anyway, so the rational homotopy groups, you simply take pi k of x, you tensor them with Q. The tensor is over Z, obviously. And you place them in degree k minus 1, okay? Why are you placing them in degree k minus 1? Well, for the simple reason that the Whitehead bracket decreases degree by 1, right? You start with degree k, degree L, and the output is k plus L minus 1. To adjust that, to make the bracket of degree 0, you basically do a shift. And we have seen this shifting business in a lot of the other talks as well. So you take this is now a rational vector space, you place it in degree k minus 1, and they form a Lie algebra over Q, a graded Lie algebra, okay? So now there's this adjunction, which was discussed earlier, that you can compare the k plus 1th homotopy group of X, and that can be identified with the kth homotopy group of the based loop space. So you can transfer the Whitehead bracket onto this side and talk about what you get here. And the advantage of doing it here is that it already takes care of the shift. Okay, so this one is placed in degree k, so this is already in degree k. So this makes everything like natural. Okay, so we have a Lie algebra Lx, which is simply take the rational homotopy groups of the base loop space and then transfer the Whitehead bracket onto this side. There is some issues of signs that you have to take care of, but it can be done. Okay. So a few examples of what this bracket does. So this is, I'm going back to the usual Whitehead bracket, and this is a quick review of some very classical things. If you take the identity Whitehead bracket with identity, where identity is just the generator of pi2 of S2. This is 2 times eta, where eta is the half map. Okay. So the Whitehead bracket of identity with identity is non-zero. In fact, it generates an infinite cyclic group inside pi3 of S2. And the same is true in general if you talk about identity map from even spheres to itself. On the other hand, if you take a generator of pi2 of CPN, remember pi2 of CPN is generated by a line inside CPN or a copy of CP1. And so if you take S2 to be a copy of CP1 inside CPN, call that map alpha. Then you can check that alpha alpha bracket is 0. Why is that? Because this by definition will be an element of pi3. And my n is at least 2. And for such CPNs, one knows that pi3 of CPN is 0. So one way of seeing that is to use the long exact sequence of the circle fibration, where Cpn is the base, S2n plus 1 is the total space, and S1 acts on S2n plus 1, right? And so the third example is if G is a Lie group, well, what happens? Well, so this is something all of you must have seen in algebraic topology or algebraic topology, that the fundamental group is abelian. So the commutator is 0. But even otherwise, if I am given two maps, alpha and beta, from Sk to G and Sl to G, we can form the product. And one can check that this is an extension of the bracket alpha beta, because you can now multiply things in the target, because the target is group. So in particular, we realize that all the Whitehead products are 0 for a Lie group. Okay, and it's true even for an H space, but I'm just stating it for what we are going to need later. Okay, any questions before I do some examples? Okay, yeah. So let's do the example of a sphere. So I'll just do it for the odd spheres. You can similarly work out the case for the even spheres. So if I want a minimal model along with all these data of looking at this D1, which is, oh, so by the way, I didn't quite say, I didn't mention it here, but I should mention. So when we talked about D1, remember, if I just let me take 1 minute more and talk about this. Yeah, so I talked about this thing and I said that this is a Lie bracket, but now for vector spaces over Q. So this is nothing but you take the usual, so here you take this Lie algebra Lx, this has a Lie bracket, which is the Whitehead bracket transferred, or you can take the usual Lie bracket on the Whitehead, generated by the Whitehead bracket on the usual homotopy groups of X tensor Q. So that Lie algebra structure is nothing but the structure that we obtain from D1 star, or obtained from D1. Okay, so the D1 of the minimal model, the quadratic part is capturing the rational Whitehead bracket. That's the point. Okay. So yeah, so if you take spheres, for example, how do I construct a minimal model? Well, we know the cohomology of spheres, right? So H upper 3 of S3 with Q coefficients is Q. So you just choose a generator omega, choose an element omega in the piecewise polynomial form such that this generates the top cohomology. And then you simply take a formal DGA, which is of the form omega x comma 0, 0 differential, x is in degree 3. And all it does is maps x to omega. And because this is graded commutative, x square is 0. And so this is a quasi-isomorphism. Okay, so this is a minimal model for S3. And this is fine because we saw already by Sayre's result that pi 3 of S3 tensor Q is Q. Every other rational homotopy group is 0. So this agrees with that. Okay. For S2, you can consider the same thing. You can take this model. You need one generator in degree 2 and one in degree 3 so that dy is x square. And the reason is because x is in degree 2. So x square is not 0. It's because graded commutative says x square is x square. So I have to kill that because there is no cohomology in degree 4. And to do that, you have to introduce a y. And it's the same setup. You choose a omega, which generates the second cohomology of S2. Choose a y. You have to choose a eta, which basically whose d will be omega square in the APL model, and that's it. Okay. So, and the same thing works for odd spheres and even spheres in general. You can work it out. And so the fact that this y exists is saying that the Whitehead product of identity with identity is non-zero. So rationally, the Whitehead product of identity with identity is a generator of pi 3 of S2, right? So that's essentially being captured by this relation. Now, what about Lie groups? Well, let's stick to compact connected Lie groups. So by Hoff's work, one knows that the real cohomology is a free algebra generated by odd generators, finitely many. And so once you know this, you already know what to do. I mean, the minimal model really looks like a free graded commutative algebra on a vector space V, which have components only in odd degrees. Okay, and then you can map it by the same kind of method. So in particular, if you wanted some concrete examples, minimal models for UN and SUN are given by free graded commutative algebra generated on x1, x3, x2n minus 1. The differential is all 0. And for SUN, because it's simply connected, you only start with x3 through x2n minus 1. There's no x1. This x1 is capturing the fact that pi 1 is z. Okay? So yeah, and this, because the differential is 0, the quadratic part is 0, which says that the rational Whitehead product is, and the bracket is 0. But we knew that the Whitehead bracket is 0 anyway. So this is a connection. Okay. So yeah, so I'll stop here. If there are any questions or comments.
So now just a question now maybe. So when you do, if you just follow the recipe you gave for constructing the model for S2, so literally you would get dy is x square over 2, right? Because what you said about the bracket on the identity being twice the class.
Just a second.
I mean, it makes no difference. I'm just curious because it sort of resonates with me for some other reason.
I see.
You explained that if you take the bracket.
Okay. Yeah, so here, okay, I guess the point is right. So, I mean, the way this is constructed, you choose a y to map to eta so that d eta is, so omega squared is cohomologous to 0. So omega squared is going to be d eta for some eta because there's no fourth cohomology. And so you choose a generator y, I mean, you choose a formal generator y and you map y to eta. So that determines the map from the left-hand side. So now your question is, so if I look at the quadratic part of this, then this is the quadratic part, right? So yes, so
right,
yeah, so your remark would be that yeah, so if x did correspond to the like the iota or the identity map,
correct.
It should say that iota is not necessarily going to give you this eta. I mean, there's going to be a factor. Yes, you're right.
No, yeah, because it sort of
so this
relates to something we see.
Yeah. So there's going to be a factor, yes, but then that is invertible in Q. But yeah, the
of course,
may not be exactly what you have. Yes, right.
Okay, very good. Okay, thanks.
Srikanth, are you thinking about divided power algebra?
Exactly. Because in local algebra, what you would do is kill x square over 2 rather than x square.
So this is like the divided polynomial rings or something like that.
Yeah, exactly.
Okay. I see.
Somnath, there's a question in the chat. Maybe we can answer that and then go to.
Just let me. Just a second. Let me open the thing. Can I stop sharing? I cannot. I can now see chat. Yeah. So two spaces are rationally homotopy equivalent. Then they have isomorphic Lie algebra. But the converse is true. So by the converse, you mean that. So I mean, see, one would ideally want. See, I mean, the point is, if you take, for example, RP 3 and S3, right? So if you look at the rational homotopy groups, they're the same, correct? So you're saying if you have isomorphic Lie algebras, that is fine. And so they're just maps of Lie algebras, or they're induced by some sort of a map. I mean, if they're just isomorphic Lie algebras, I don't.
Lie algebra, but different rational homotopy type. Is this a complete invariant?
No. Again, I think the issue would be if there's the relevant question would be if there's a map at the level of spaces or base group spaces which induces isomorphism. Because if you have abstract Lie algebras, even if they came from spaces, I mean, if they're isomorphic, I don't see why the spaces would be sort of. I mean, you can ask this question even in the context of just spaces. Forget rational spaces. Take X and Y and ask whether homotopy equivalent is detected by looking at the Whitehead Lie algebra over Z or over Pi.
Yeah, I think the point is you have to lift it to the DG Lie algebra from the, I mean, you have to lift it to the Lie model. If you can lift it to the Lie model, I think you can get a rational map. Then, and once you have a rational map, if it induces an isomorphism, then
then you have
then you have it.
Okay, we can postpone other questions to the discussion maybe.